You're listening to Introduction to Philosophy of Science. This is part 2 of Cosmology and Epistemology. In the previous video, we explored cosmology. If you haven't been exposed to philosophy of science before, when you watch that video, you might say to yourself, wait, I thought only scientific results can be considered true. Isn't everything else, like mythology, is just made up or untrue? If you're asking that question, you are stepping into a philosophical field called epistemology. Epistemology is the study of knowledge. It covers three main questions. First, the nature of knowledge. What exactly do we mean when we say we know something? The second question is the sources of knowledge. Where does our knowledge come from? Is scientific experimentation our only source of knowledge? Or are there other valid ways of knowing? And third, the limits of knowledge. How far can science inform us about reality? What boundaries or what questions exist that science simply cannot address? When you study epistemology, you see the strengths and weaknesses of science, and it makes you a better thinker about science, and that helps you engage with scientific information in daily life. One important position in epistemology is called empiricism. So this is the dominant epistemological position among natural scientists. In philosophy of science, when we talk about empiricism, we mean that the idea that our knowledge comes only from what we can observe and experience with our senses, our external senses. I usually think of this like a 5-star hotel chef. So they rely on their sense of smell, their sense of sight, their sense of taste to judge the quality of their dishes. So just like that chef, empirical scientists trust their senses. They trust their eyes, their ears, and other senses using instruments to gather reliable information about the world. So they don't trust ideas unless those ideas can be supported by what they can directly observe through senses. You can contrast empiricism with another epistemological position called rationalism. For this one, I think of Doctor Strange from Marvel Cinematic Universe. So there's a moment in Infinity War where Doctor Strange calculates millions of outcomes before fighting Thanos. So that's not empiricism, right? He did not experiment using external senses. He gains knowledge through rational intuition. So rationalists argue we can gain knowledge through intuition and deduction. And unlike empiricism, rationalism says we can uncover truth beyond what our senses directly experience. So most intellectuals you meet will position themselves somewhere between rationalism and empiricism. So understanding this will help your professional communication with them on deeper issues, especially about science and religion. Another epistemological issue in science is the debate between realism and anti-realism. So one key question in that is, does science give us true knowledge, or at least approximately true knowledge? If you are a pure realist, you're going to say, yes, absolutely. Even things that we cannot directly observe, like electron cloud or immunological synapses, if they are successful scientific theories, they represent reality as it truly is. Anti-realists disagree with that. They suggest that science gives us useful thinking models, useful theories to predict the world. They are not necessarily truths about reality. So scientific theories are valuable because they are useful, not because they are true. Realism in science argues that the entities that our theories describe actually exist. They're actually there, independent of our thoughts or observations. So for realists, successful scientific theories don't just work well, they also accurately describe what's really out there. Right? So this includes observable entities like planets or organisms, but also unobservable entities such as quarks or genes. So you cannot directly observe quarks. Think of quarks like Lego blocks that are tightly glued together to form a structure. So you can't separate one block easily because the glue, the strong force, gets stronger as you pull. So we don't see this phenomenon physically in the labs. We only see their effects in particles like neutrons. Genes are similar. You can't directly observe a gene itself. Genes exist as instructions within DNA. So you don't physically see a gene, but you clearly see its effects on organisms, the phenotypes of the organisms. Why do realists think they are right? Well, science has an impressive track record of predicting natural phenomena. So if scientific theories don't describe something real out there, how come we can do so, right? So this is a strong philosophical argument called the no miracle argument. It says that the success of science would be miraculous, would be magical, if our theories were not at least approximately true. So the reason we can accurately predict phenomena is that our theories correctly reflect reality. The problem is, when you look at the history of science, it shows us that theories can successfully predict natural phenomena at one time, but later be found to be false. There are two well-known examples. First is the phlogiston theory. So in the 18th century, this theory explained combustion by an invisible substance called phlogiston. So this phlogiston is released when we burn materials. It accurately predicted burning outcomes. However, later it was considered wrong and replaced by our current oxygen-based combustion theory. So that's example number one. The second example is Newton's theory of gravity. For centuries and centuries, scientists believed in gravity as an invisible force pulling objects towards each other. So for example, Newton would say the Earth orbits the Sun because there's an invisible gravitational force pulling them together, right? Later, the theory of general relativity provided a different picture. So according to Einstein, the Sun's mass, because it's so big, it curves space-time around it. So there's no invisible force pulling the Earth, like what Newton said. Instead, the Earth simply moves along the curved space-time created by the Sun. So these historical cases and many others like them suggest that scientific theories can be useful. Scientific theories can be predictive, but they may not correctly reflect reality. One alternative to realism is instrumentalism. Instrumentalism argues that scientific theories are instruments, they're like tools for predicting natural phenomena. They're not literal claims about reality, independent of your mind. It's a more modest position. So it says what matters most isn't whether theories reflect reality, but whether they effectively help us predict the world. So this perspective explains why theories like phlogiston and Newtonian gravity lasted for so long. It's not because they are true. Even though they were later considered incorrect or incomplete, they persisted because they were practically useful for making accurate predictions. So today, for example, immunologists use a theoretical framework called self versus non-self. The idea is that if a substance is a self, like your own cells, your immune system tolerates it. If it's a non-self, like bacteria, your immune system attacks it. But is that literally true? Well, not always. Our immune system sometimes attacks our own cells, like what happens in autoimmunity, and our immune system can tolerate non-self bacteria in our gut. So what's the truth? Instrumentalist immunologists would say, I'm not claiming this theory is literally true or the correct representation of reality. What I'm saying is, this theory is valuable because it reliably helps us predict immune responses. Now, between realism and instrumentalism, there is a practical middle ground called constructive empiricism. Constructive empiricism agrees partly with realism. It says scientific theories do talk about something real outside our minds, but it's different from realism in one important way. It doesn't say our theories exactly describe reality. Instead, constructive empiricism says our theories are models, and these models only need to be empirically adequate. Also, what's empirically adequate? It just means the theory works well enough to predict things we can actually observe. So think again about the immune system example, self versus non-self. A constructive empiricist would say, yes, we can use this model because it accurately predicts how the immune system reacts. But we're not saying self and non-self literally exist exactly as described. They are just useful ideas. Constructive empiricism keeps things practical. It appreciates science for referring to reality, but stays careful about claiming too much about things we can't directly see or directly observe. All right, let's wrap this up. The main idea here is simple. As a scientist, you don't have to fully believe that your theories describe reality exactly as it is. You don't even have to believe things like electrons or quarks or genes exist exactly the way we talk about them. Your main commitment is just that your theories work. They help you reliably predict what happens, predict how to do experiments, and help you move your science forward. So, this practical attitude doesn't weaken science at all, by the way. Actually, it makes science stronger. Because if new evidence shows up, you stay flexible. You adjust, you refine, or even replace your theories. So, in your own thinking, in daily life, you remember this perspective. You don't need to be overly attached to any scientific theory. Think of theories as powerful tools. You use them confidently, but you stay ready to update your understanding whenever reality shows you something new. That's all for this topic. Keep on reading, keep on learning. Barakallahu li wa lakum. Wassalamu alaikum warahmatullah.